Alright, let's get started. We begin today's class with a question on degrees of unsaturation. You can pause the lecture here to answer the question. Alright, let's take a look at this question. Find the degrees of unsaturation for the molecule below. As we have learned in the last lecture, degrees of unsaturation is nothing but a combination of all the pi bonds and the rings in a molecule. So let's count the number of pi bonds and rings here. You have one pi bond here in that double bond, another pi bond here in that double bond. That is one ring. That is the second ring. So you have two rings and two pi bonds. That's a total of 4. So the degrees of unsaturation in this molecule are 4. So as you can see, just by looking at the molecule, it is very straightforward to figure out the degrees of unsaturation. Alright, count the total number of pi bonds and the total number of rings. That will be equal to the degrees of unsaturation. In the last lecture, we began chapter 7, that is alkenes. We briefly looked at the structure of alkenes and the degrees of unsaturation. So let's continue with the structure of alkenes. Let's look at what is called cis-trans isomerism. Hindered rotation across C double bond C results in geometric isomerism in alkenes. So let's understand what that statement means with the help of these two molecules as the examples. So let me write out the structure of these two molecules. C double bond C, each of them have a hydrogen, and you have CH3 on each of the carbon. If you write this molecule, again C double bond C, CH3 and CH3. Now, as I showed you in the last lecture, due to the presence of these double bonds in alkenes, you cannot freely rotate across that carbon-carbon bond. As a result of that, you can have two groups bonded to the double bonded carbons on the same side or on the opposite side of the double bond. Groups on the same side of the double bond, you will call that molecule cis. Groups on the opposite side, you will call it as trans. And like we learned in chapter 4, cis and trans are stereoisomers because they only differ in arrangement of groups in three-dimensional space. So let me show you cis-trans isomerism with the help of the models. So what I have here is the cis isomer. These carbons are the double bonded carbons. Each of the double bonded carbon has a hydrogen and a CH3. But as you can see, both the CH3 groups are on the same side of the double bond. And that is why this is a cis isomer. Let's now look at trans. So this is the trans isomer. Again, these are your double bonded carbons. Each of the double bond carbon has a CH3 and a hydrogen. But now the CH3s are on the opposite side of the double bond. And that's why this is called a trans isomer. Now let's see why cis and trans are called stereoisomers. Now if you take a look at both these molecules, each of the double bonded carbons have the same groups attached to them. This carbon has a hydrogen, CH3. This carbon to here has a hydrogen, CH3. This carbon again hydrogen, CH3. This carbon hydrogen, CH3. So the atom connectivity has not changed between these two molecules. And that is why cis and trans are not constitutional isomers. When you have the same atom connectivity, they are not constitutional isomers. The reason they are stereoisomers is because they only differ in arrangement of groups in three-dimensional space. If you take a look at this carbon, it's attached to hydrogen and CH3. Here too, this carbon is attached to hydrogen and CH3. But how it's arranged in space is different. Here you have the hydrogen up, here you have the hydrogen down. CH3 down, CH3 up. So since these two molecules differ in arrangement of groups in three-dimensional space, these two molecules, cis and trans, are called stereoisomers. Alright? Now there's no way you can convert cis to trans by bond rotation. The only way I can convert cis to trans or trans to cis is by breaking a bond and forming a new bond. Let me show you that. Let's say I have this molecule that is a cis. I want to convert it to trans. Don't break the bonds for both the groups. Break only the bond for one of the group. So let's say I take this carbon that has the CH3 here. To make it trans, I need to break this bond and the hydrogen, put the hydrogen on this side and put the CH3 on this side. Right? Now this is a trans isomer. Right? So as you can see, the only way I can convert cis to trans or trans to cis is by breaking bonds and making new bonds. Alright. So let's now get back to the slides. So key points of cis-trans isomerism: groups on the same side cis, groups on the opposite side trans. Cis and trans are stereoisomers. The only way you can convert cis to trans or trans to cis is by breaking bonds and forming new bonds. Alright. So let's take a few examples on cis-trans molecules. Now when you're learning how to label cis and trans, write out the atoms. Hydrogen, hydrogen, CH3. Groups on opposite side of the double bond, this is trans. Groups on same side of the double bond, this is cis. Now whether I write the molecule like this or I write the molecule like this, both these molecules are exactly the same. This is also cis. All I've done is taken this molecule, rotated in the plane of the paper and shown it like this. But both those molecules are exactly the same. So as you can see, labeling a molecule cis or trans is very straightforward. Groups on the same side of the double bond cis, groups on the opposite side of the double bond trans. But you can use cis-trans nomenclature only when you're looking at the relationship between two groups. Once you go beyond two groups, you cannot use cis-trans relationship. Let me show you an example. Let's say I have this molecule. Now as you can see, for this molecule, on the double bonded carbons, you have 3 groups in total. So you cannot use cis and trans for that. Cis and trans works only when you're comparing the relationship between 2 groups. Right? So what happens when you go beyond 2 groups? How do you name the molecule? The nomenclature system we use when we go beyond 2 groups is called the ENZ designation. So let's now look at rules to assign ENZ configuration. The first step to assign ENZ is to draw a perpendicular line to the double bond. So this is the double bond, draw a perpendicular line. And you're going to evaluate each of the carbon. So let's say I'm evaluating this carbon. It has nothing to do with the other carbon for now. Look at that carbon, one carbon of the double bond, and assign priorities to the groups attached to it. I will discuss the priorities in a minute. So let's say I'm evaluating this carbon. I have the higher priority group here and the lower priority group here. Perform the same evaluation for this carbon. I have the higher priority group here and the lower priority group here. Right? So draw a perpendicular line, look at either of the carbons individually, and for each of the carbons assign priorities. Right? And once I assign priorities, let's say the higher priority groups are on the same side, that configuration would be Z, like cis. Once I assign priorities, let's say the higher priority groups are on the opposite side, then that would be called an E configuration, like a trans. Right? As we take examples, this will become clear to you, assigning E and Z. So let's take an example. Let's say you're given that molecule and you need to assign E or Z for that molecule. Now follow these steps carefully always, you will get the correct answer. So let's go through step 1 to 4. First step, draw a solid line perpendicular to the alkene. So you're looking at the double bond and drawing a perpendicular line to the double bond. Right? So this is the double bond, you're drawing a perpendicular line. Assign priorities to both groups on either side of the line. Once you draw that perpendicular line, look at each of the double bonded carbons individually, okay, to assign priorities. And the priorities are exactly like your R and S, based on atomic number. Higher the atomic number, higher the priority. Okay. Look at the first atom attached. If it is different, you can right away assign the priorities there. If the first atoms are the same, go further along the chain, find the point of difference to assign priorities. All right. So now let's take a look at this carbon. You're evaluating the groups on that carbon. You have a bromine and a CH3. Bromine has higher atomic number than CH3, so bromine gets priority 1, CH3 gets priority 2. Now you never go beyond 2 number. You have only 2 groups attached to a double bonded carbon. Right? So priority 1 and 2, that's it. You'll not go beyond 2 priority. Right? Let's now take a look at this carbon. The groups attached to that carbon are hydrogen and chlorine. Hydrogen gets priority 2, chlorine gets priority 1. Chlorine has higher atomic number than hydrogen. Now the last step, once you have assigned priorities, is to draw a dotted line parallel to the alkene to find if it's E or Z. So let's do that. You're drawing a dotted line parallel to the double bond. Once you have drawn the dotted line, look for where the higher priority groups are located. The higher priority groups are on the same side of the dotted line, which means this is a Z. All right. So if you follow these steps, it's very straightforward to assign E and Z. Let's take another example. First step, draw a perpendicular line to the double bond. At each carbon, assign priorities. So for this carbon, bromine gets priority 1, CH3 gets priority 2. Bromine has higher atomic number than CH3. For this carbon, chlorine gets priority 1, hydrogen gets priority 2. Draw a dotted line then, parallel to the double bond. Look for the higher priority groups. They are on the opposite side of the double bond, so this is an E. All right. Let's take a few more examples. Again, begin by drawing a perpendicular line to the double bond. At each of the double bonded carbon, assign priorities. Hydrogen priority 2, CH3 priority 1. At this double bonded carbon, this is CH2 attached to CH3 if I write it out. This is a CH3. A CH2 attached to a carbon gets more priority than CH3. So this gets priority 1, this gets priority 2. Draw a dotted line parallel to the double bond. Look for the position of the higher priority groups. They are on the same side of that dotted line, therefore this is a Z. Let's take another example. First step, draw a line perpendicular to the double bond. Assign priorities to each of the double bonded carbon. Now if you take a look at this carbon, you have the same groups. So you can't decide between priorities for those two groups. Both are CH3. So this molecule has no E or Z. E and Z is possible when the carbon of the double bond is attached to different groups. Here both the groups are CH3. You can't give priorities to those. They are the same groups, right? So there's no E and Z for that molecule, right? Let's take another example. Draw a line perpendicular to the double bond. Assign priorities 2, 1, 2, 1. Draw a dotted line parallel to the double bond. Look for the higher priority groups. They are on the same side of the dotted line. This is Z. Again, start with a perpendicular line to the double bond. At each carbon, give priorities. At that carbon, CH3 gets 1, hydrogen gets 2. At this carbon, this is CH2 attached to a nitrogen. This is a CH3. So CH2 attached to a nitrogen gets 1, CH3 gets 2. Draw a dotted line parallel to the double bond. Locate the higher priority groups. They are on opposite side of the dotted line, so this is E. So if you follow the steps I've mentioned in the previous slide, you will not go wrong in assigning E and Z. And please keep in mind the priority rules are exactly like what you've learned with R and S. Alright. So let's take a few more examples on E and Z. This is the first example. You can pause the lecture here to answer this question. So let's take a look at this question. Assign E and Z designation to each of the molecules below. So let's look at molecule A. First step, draw a line perpendicular to the double bond. Each of the carbons assign priorities. For this carbon, this is a CH3. This is a carbon attached to an oxygen, OH. So this gets priority 1, this gets priority 2. For this double bonded carbon, hydrogen gets priority 2, fluorine gets priority 1. Fluorine has higher atomic number than hydrogen. Now draw a dotted line parallel to the double bond. Locate the higher priority groups. The higher priority groups are on opposite sides of the dotted line. Therefore, this is E. Opposite sides is E. Same sides is Z. All right. Let's now take a look at molecule B. Again, begin by drawing a perpendicular line. At this carbon, you have a bromine and chlorine. Bromine has a higher atomic number than chlorine. So this gets 1, this gets 2. This side you have a CH3, up you have a CH2, CH3. So for this carbon, CH2, CH3 gets priority 1, CH3 gets priority 2. Once you have assigned priorities, draw a dotted line parallel to the double bond. Locate the higher priority groups. They are on opposite side of the dotted line. So this molecule is also E. So the answer to the question, Both the molecules are E configuration. All right. So let's take another example. Again, you can pause this lecture to answer the question. So this question too is, given these two molecules, you need to assign E and Z configuration. So let's begin by taking a look at molecule B. First step, draw a line perpendicular to the double bond. Let's take a look at this carbon to assign priorities. You have a hydrogen and bromine. Bromine has higher atomic number, so it gets priority 1, hydrogen priority 2. Let's now take a look at this carbon. First, you have a CH2 attached, here too a CH2 attached. Then you have a nitrogen, here too nitrogen. So far there's no point of difference. I cannot assign priorities yet. So go further along the chain. Here you have two hydrogens, you have one hydrogen and a carbon. Hydrogen and a carbon gets higher priority than two hydrogens. So this would be priority 1, this would be priority 2. So now that we have assigned priorities, draw a dotted line parallel to the double bond. Locate the higher priority groups. They are on opposite side of the dotted line, therefore this is E. Let's now take a look at molecule A. Again, begin by drawing a line perpendicular to the double bond. Let's assign priorities. For this carbon, you have a hydrogen and CO2H. Hydrogen gets priority 2, CO2H gets priority 1. Now for this carbon, if you want to assign priorities, this side you have a CH2, this side too you have a CH2. So as of now, both are the same, both are CH2. So go further along. This side you have a carbon that's attached to a CH3 and a carbon. This side you have a CH2. So that is your point of difference. Down you have a carbon attached to a CH3 and one hydrogen. Top you have a CH2. So this gets higher priority. So this side gets priority 1. This side gets priority 2. Once you have assigned priorities, draw a dotted line parallel to the double bond. Locate the higher priority groups. They are on opposite side of that dotted line, so this is also E. So both these molecules are again E. Right? So please practice assigning easy configuration. These are very simple, straightforward questions. All right? Let's now look at alkene nomenclature. Whenever you are naming an alkene, the suffix "ene" is added to show that it's an alkene. For alkane, we added "ane" to show it's an alkane. For alkene, you're adding an "ene" to show it's an alkene. Let's take an example. Let's say I have this molecule and I want to name it. The rules are very similar to what you have learned with alkanes. First step, figure out the longest hydrocarbon chain, the parent chain. 1, 2, 3, 4. So this is a 4-carbon chain. Now you can number this 4-carbon chain this way, the way I've shown you, or you can number it like this. The correct way of numbering is to give the double bond lower numbers. Right? So the red way of numbering is correct because the double bond is getting number 1 and 2. In this way of numbering shown in black, the double bond is getting 3 and 4. Right? You want to give the double bond lower numbers. So the red way of numbering is the correct way of numbering. It's a 4-carbon chain. 4-carbon is bute. Because it's an alkene, you're going to call it butene. The last step now is to add the position of the double bond. The double bond is starting at carbon number 1. So this is 1-butene. Let's take another example. First step, count the longest hydrocarbon chain. 1, 2, 3, 4. Now whether you start 1 in this direction or from this direction, the double bond is going to get the numbers 2 and 3. right? So either way you number, you're going to get the same numbers on the double bond, all right? So this is also a butene because it's a 4-carbon chain. Alkene means ene, so butene. Let's add the position of the double bond. The double bond is starting at carbon number 2, so this is 2-butene, right? Now one last thing you need to add is whether it's cis or trans. Because the groups are on opposite side of the double bond, this is a trans 2-butene. All right. So when you're naming alkenes, the 2 additional steps you will have is to write the position of the double bond as well as to mention if it is cis or trans. All right. Let's take another example. Let's say I want to name this molecule. Again, let's figure out the longest chain. 1, 2, 3, 4. It's a 4-carbon chain. So again, you're looking at butene. The double bond is starting at carbon number 2. So this is 2-butene. The last step is to add the position of the substituents. So at carbon number 2, you have a CH3. At carbon number 3, you have a CH3. So 2,3-dimethyl 2-butene. There is no cis or trans or E and Z here because the carbons are attached to the same groups. Right? So for every name, you will not have cis and trans or E and Z. Depending on the structure, you will have cis and trans or E and Z. All right. Let's take another example. Let's say I want to name this molecule. Again, first step, figure out the longest hydrocarbon chain. 1, 2, 3, 4, 5, 6. So the parent chain is a 6-carbon chain. Now you can number it this way, or I can number it this way. Now either way I number it, the position of the double bond and the substituents is exactly the same. You can take a look. In the black way of numbering, the double bond is between carbon 3 and carbon 4. In the red way of numbering 2, the double bond is between carbon 3 and 4. In the black way of numbering, the substituents are at carbon 5. You have 2 substituents, CH3 and CH3. At carbon 2, you again have 2 substituents, CH3 and CH3. In the red way of numbering, at carbon 2, you have 2 CH3s. At carbon 5, you again have 2 CH3s. So as you can see, the position of the double bond as well as where the substituents are attached is exactly the same. Either way you number the chain, right? So you can use either one, you will get the same answer. So the longest hydrocarbon chain is 6-membered, so this is hexene. The position of the double bond starts at carbon number 3, so this is 3-hexene. Right? Let's now add the position of the substituents. You have 2, 2, 5, 5. You have 2 metal groups at position number 2 and 2 metal groups at position number 5. So it's 2, 2, 5, 5. 4 metals in combined, so tetramethyl. Hexene. That name accounts for all the substituents and the parent hydrocarbon as well as the double bond position. The last step is to assign cis-trans or E and Z. As you can see here, you have 2 groups on the opposite side of the double bond. So this is trans. So the overall name of this molecule is trans 2255 tetramethyl 3-hexene. All right. Let's take one last example on nomenclature. Let's say you need to name this molecule. As you can see, it's a 6-carbon ring. A 6-carbon ring without the double bond is cyclohexane. This has the double bond, so this is cyclohexene. And you don't need to mention the position of the double bond in the name, because wherever you're starting the double bond, that is understood to be carbon 1. All right. So you don't need to write the position of the double bond, you just call it cyclohexene. Also, what you don't need to write is whether it's cis or trans double bond. In a cyclohexene ring, you can have only a double bond if it is cis. You cannot have a trans double bond in a cyclohexene ring. That's why you don't mention cis or trans. If I try to have a trans double bond, I cannot form the ring. This end is very far from this end, so you can't form the ring. So in a cyclohexene ring, the double bond will always be cis. All right. So you just call that molecule as cyclohexene. All right. All right, let's now move from alkene nomenclature to alkene stability. The stability of an alkene is given by the heat of hydrogenation value. Heat of hydrogenation is also referred as change in enthalpy of hydrogenation. Change in enthalpy is delta H. A subscript of HYDROG stands for hydrogenation. So this is the symbol for change in enthalpy of hydrogenation. Let's first define what it is, then we'll understand it. It is the change in enthalpy which occurs when 1 mole of unsaturated compound reacts with excess hydrogen to become fully saturated under standard conditions of atmospheric pressure and room temperature. Since the reaction is performed under standard conditions, you have a superscript naught in the symbol to signify that. All right. So this is the definition of heat of hydrogenation. So let's understand what this definition means with the help of an example. What I have here is 3 compounds. Let me call them A, B, and C. And all these 3 compounds have the same number of carbons. Each one of them has 4 carbons. And also each one of them has 1 double bond. Now, if I want to figure out the heat of hydrogenation of these compounds, I have to react each one of them with excess hydrogen and convert the unsaturated compounds to saturated compounds. These are unsaturated compounds because they have at least a double bond. Upon reaction with excess hydrogen, I'm going to convert them to saturated compounds. No double bonds in the products. And all these 3 compounds, A, B, and C, will give you the same product butane. And essentially what you're doing in this reaction is adding hydrogen atoms to each of the double bonded carbons, thereby converting unsaturated reactants to fully saturated products. And the change in enthalpy associated for this reaction is called the heat of hydrogenation. So let's look at the values for these 3 compounds. Minus 126 kilojoule per mole, minus 116 kilojoule per mole, minus 120 kilojoule per mole. Now, 2 key points about heat of hydrogenation. First, it's always a negative value, which means energy is always released in this reaction. Products are more stable than the reactants. Products have lower energy than the reactants. All right. The second point is that more the stability of the alkene, the lesser is the absolute value of delta H. So among these 3, if you take a look, this has the least absolute value. This is the most stable alkene. This has the highest absolute value. This is the least stable. and alkene C is in the middle. That's how, looking at the heat of hydrogenation value, you can figure out alkene stability. Lesser the absolute value, more the stability of the alkene. Higher the absolute value, lesser the stability of the alkene. So let's first take a look at the difference between molecules A, B, and C. Molecule A, if I name it, will be 1-butene. Molecule B and C both are 2 butenes. 1, 2, 3, 4, 1, 2, 3, 4. The double bond is starting at position number 2 for both B and C. So both are 2 butenes, but B is trans 2-butene. As you can see, the groups are on opposite side. C is cis 2-butene. Now, if you look at the difference between A versus B and C, A is called a terminal alkene. Terminal alkene means the double bond will be at the end of the chain, will be at the end of the molecule. So those kind of molecules are called terminal alkenes. B and C are internal alkenes. Internal alkenes because the double bond is within the chain. It's not at the end of the molecule. Right. So A is a terminal alkene. B and C are internal alkenes. Among B and C, B is a trans, A is a cis. Now, looking at these values, if you write the stability order, the most stable has the least value. So trans is the most stable. The least stable has the highest absolute value. So the terminal alkene is the least stable. And cis is in the between. So that is the stability order for compounds A, B, and C. And you have come to that order looking at these values. All right. So always keep in mind this statement. More the stability of the alkene, the lesser is the absolute value of heat of hydrogenation. All right. So let's now see with the help of reaction coordinate diagram why an alkene that is more stable releases less energy. All right. So here is the reaction coordinate diagram. Y-axis energy, x-axis progress of the reaction. Now all these three compounds gave the same product upon reaction, butane. So that's your product. So let's start off with the most stable reactant, which is compound B, that is trans 2-butene. As you can see, I have written the reactant higher in energy than the product. All these reactions released energy, which means reactants are higher, products are lower. The product is more stable than the reactants. That's why I've written butane at a lower energy, the product, compared to the reactant. All right. Always keep in mind an exothermic reaction will have a negative delta H. Products are lower, reactants are higher. All right. Now if I draw the graph, this is the graph for the reaction, and the delta H is the difference in energy between products and reactants. And for this reaction, for compound B, the value is minus 116 kilojoule per mole. Let's now take a look at the least stable compound among the three, which is compound A, the terminal alkene. And if you draw the reaction graph for that, this will be the graph. The difference in energy between the products and the reactants is the delta H. So this value is the delta H, which is minus 126 kilojoule per mole. So from this graph, you can clearly see why a more stable compound releases less energy, and a less stable compound gives out more energy. When a compound is more stable, it's already lower in energy. It is closer to the product. So the difference is a small value. So only that much amount of energy is released. When you have an unstable compound, it's higher in energy, so the difference between the reactant and product is a much larger value. Alright? And that is why more the stability of the compound, lesser is the absolute value of heat of hydrogenation. Lesser the stability, more is the value of heat of hydrogenation. Alright? Now if you add compound C in this graph, it will be between compound A and B, the cis-alkene. So that would be the graph for cis-alkene. The delta H would be the difference between the products and the reactants, and in this case it's a value of minus 120 kilojoule per mole. Right. Now looking at this graph, we need to answer two questions. First, why is a trans-alkene more stable than a cis-alkene? As you can see here, B is trans, it is more stable than C, which is a cis. So why is a trans-alkene more stable than cis-alkene? That's question number one we need to answer. Question number two, why are internal alkenes more stable than terminal alkenes? So as you can see, B and C, which are internal alkenes, they are more stable, they are lower in energy compared to the terminal alkene A. So let's first answer question number one. Why are trans-alkenes more stable than cis-alkenes? The simplest answer to that is sterics. Let's take the example of compounds B and C. This was compound B, it was trans, groups on opposite side. This was compound C, groups on the same side, therefore cis. Now when you have a cis double bond where the groups are on the same side, they are going to fight for space, they're going to bump into each other. On the other hand, in a trans double bond, the groups are far enough, they are on opposite side, so they're not fighting for space. That is why a trans double bond is more stable than a cis double bond. Always keep in mind, as we have learned in previous chapters, sterics means groups fighting for space. In a cis double bond, the two large groups are on the same side, they're going to start to fight for space. A trans double bond, the groups are on the opposite side, so there is no steric repulsion, so trans is more stable. Right. So let me show you this with the help of the model. So here is your cis-2-butene molecule. These two carbons are the double bonded carbons. As you can see, the CH3 groups are on the same side of the double bond. Therefore, this is a cis configuration. And if you take a look, these CH3 groups are bumping into each other for space. Right. So when you have groups in the cis configuration, there is steric repulsion because groups are fighting for space. On the other hand, if you take a look at the trans configuration, this is trans-2-butene. These are your double bonded carbons. CH3 is on the opposite side of the double bond. Therefore, this is trans configuration. Here the groups are far apart. There is no steric repulsion between the two. And that is the reason a trans double bond is always more stable than the cis double bond. Alright. So let's now get back to the slides. So the answer to the first question is steric repulsion. Let's now answer the second question. Why are internal alkenes more stable than terminal alkenes? Now before we get into answering that question, let's first understand the substitution pattern in an alkene. Now please listen very carefully here. If you have one R group attached to the double bonded carbons, that alkene is referred to as a mono-substituted alkene. if two R groups are attached to the double bonded carbons, they could be attached to the same carbon of the double bond or different carbons. Those alkenes are referred to as di-substituted alkenes. If three R groups are present on the double bonded carbons, it is referred to as tri-substituted alkenes. If four R groups are present, it is tetra-substituted alkenes. Now these R groups attached to the double bonded carbons can be same or can be different. Please keep in mind an R group is a hydrocarbon fragment, right? And now if you take a look at the stability of these substituted alkenes, the tetra-substituted is the most stable, followed by tri, followed by di. Mono-substituted is the least stable. So as the substitution, the number of R groups on the double bond increases, the stability increases, right? So let's now see why more substituted double bonds are more stable. The answer to this question is hyperconjugation. Hyperconjugation is a stabilizing interaction between the pi bond of the double bond and the adjacent sigma bonds. So let's understand what this statement means with the help of the model. So what I have here is a mono-substituted double bond. There's only one R group, one CH3 group attached to the double bond. Therefore, this compound is mono-substituted. CH2, CH, CH3. All right. So this is the pi bond in the double bond. This is the sigma bond in the double bond. Now we said hyperconjugation is a stabilizing interaction between the pi bond and the adjacent sigma bond. Now please watch carefully here. What is this interaction? So if you take a look, this p orbital is parallel to the CH bond. So this interaction is a stabilizing interaction between this p orbital and the CH bond. Right? Now keep in mind this is a single bond, so this can freely rotate. Between the double bond I cannot rotate, but this is a single bond, so I can freely rotate. Right? So each of the CH bond provides a stabilizing interaction. So an R group here provides three stabilizing interactions. 1, 2, and 3. All right. Now if you have another R group here, 3 more. Another R group, 3 more. Another R group, 3 more. So as you increase the substitution pattern on the double bond, you have more hyperconjugation, therefore more is the stability. Right? If you have just hydrogen, there is no bond parallel to this pi bond when you have only hydrogen. So there is no hyperconjugation. Only when you have an R group, you will have hyperconjugation. Now also keep in mind, you need not always have a CH3. You can even have a CH2, CH3, right? So let me put a CH3 there. So what I have here now is CH2, CH3. Even then you have the sigma bond between the two carbons. That is hyperconjugation with this p orbital, right? So anytime you add R groups on the double bond, you are increasing the number of hyperconjugations. Therefore, the stability is going up. All right. So let's get back to the slides. So the key points from this slide are that more substituted alkenes are more stable than less substituted alkenes. And the reason for that is hyperconjugation, which is a stabilizing interaction between the pi bond and the adjacent sigma bonds. Now if you go back to the example of molecule A versus B and C, molecule A was a terminal alkene. It was mono-substituted. Molecules B and C were di-substituted. Therefore, B and C were more stable than molecule A. All right. Now that we have learned about stability of alkenes, here is a question for you. You can pause the lecture for a minute to answer this question. All right, let's take a look at this question. Arrange the following alkenes in order of increasing stability, least stable to most stable. Anytime you are looking at stability of alkenes, look at the substitution pattern on the double bond. Compound C is di-substituted. It has 2 R groups. Compound B is tri-substituted. It has 3 R groups. Compound A is tetra-substituted, 4 R groups. More the substitution, more is the stability. So among these three, the most stable is compound A, the least stable is compound C, B is in the between. So that is your stability order, CBA. Right. So as you can see, questions like these are very straightforward. Anytime you're asked a question on alkene stability, always look at the substitution pattern. More the number of R groups, more is the stability of the alkene. Alright. So that finishes alkene stability. The last part of this chapter is electrophilic addition reactions to alkenes. Alkenes undergo electrophilic addition reactions. Right? We'll understand what that statement means in a minute, but let's begin by taking a look at a reaction. Let's say I have this reaction. Now, anytime you're looking at a reaction, usually reactants are written on the left side of the arrow. But sometimes you can see the reactants written above or below the reaction arrow. Solvents, temperature, reaction conditions like time of the reaction are always written above or below the reaction arrow. They're never written on the left side of the arrow. Reaction conditions are never written on the left side of the arrow. So if you take a look at this reaction, ether is the solvent in the reaction. Temperature and time is mentioned below the arrow. Alright. Solvents do not participate in the reaction. They are just present to facilitate the reaction between the reactants. Right? They are not actively participating in the reaction. Right? So let's now look at this reaction in more detail. Now, based on what you have learned in chapter 6, you can see this reaction is an addition reaction. You're starting with 2 molecules, you have 1 molecule. So you've added those 2 reactants to form one product. You're starting with a pi bond. The other reactant is HBr. You have added H to one carbon of the double bond, Br to the other carbon of the double bond to form this molecule. Alright. So this is an addition reaction. Alkenes usually undergo addition reactions. Right? Whenever you have a pi bond, always those molecules will undergo addition reactions. Alright? Let's take a few more examples. Let's say I have this compound and you're adding to this HBr. Again, this is a symmetrical alkene. What I mean by that is whether you add H to this carbon or this carbon, it doesn't matter. Whether you add Br to this carbon or this carbon, it doesn't matter. It's a symmetrical alkene. Right? So if you write the product, H to one of the carbon, Br to the other. Right? Let's take another example. Again, this is a symmetrical alkene. Both those carbons are the same. You can add H to the top carbon or to the bottom carbon. Br to the top or to the bottom. You'll get the same answer. The other hydrogens are still present. All right. Now you can use HBr or HI. This would be the product with HI. Right? So H is going to one of the double bonded carbon, the halogen is going to the other of the double bonded carbon. All right. Let's now look at the mechanism for this addition reaction. Now I want you all to pay close attention to this mechanism. This is a generic mechanism for how alkenes will react. So if you understand this mechanism, you can pretty much write the mechanism for almost all alkene reactions. All right. So let's write the reactants in this reaction, the alkene. And the second reactant I'm going to write as HX, where X can be chlorine, bromine or iodine. So these are the reactants in this reaction. And as we have learned in chapter 6, the first step when you have two reactants is to identify the nucleophile and the electrophile. Always alkenes are going to behave as nucleophiles. The reason being they have pi bonds. Pi bond has 2 electrons, so alkenes are electron rich. They're always going to behave as nucleophiles. The reagent HX can be written as H plus and X minus. So the electrophile in the reaction is H plus. Once you have identified the nucleophile and the electrophile, the reaction will take place between the nucleophile and the electrophile. Always start the arrow from the nucleophile and go towards the electrophile. So the reaction is taking place between the pi bond and the H plus. Now the H plus can go to this carbon or this carbon. It doesn't matter. Both the carbons are the same. So let's write the product. So let's say I put the H plus on this carbon. So the new bond formed as a result of this reaction is this bond. And the electrons for that bond are coming from the pi bond. A pi bond also has 2 electrons. Now as a result of this reaction, this carbon has a positive charge. It has only 3 bonds. Carbon with 3 bonds, 6 electrons is a positive charge. A positive charge carbon is called a carbocation. So this is the first step in the reaction. You have identified the nucleophile, electrophile. The alkene is the nucleophile, H plus is the electrophile. The reaction will take place between the pi bond and H plus to form the carbocation. The second step in this reaction is the carbocation reacting with the X minus. So this is the carbocation formed in the first step of the reaction. You have X minus floating around. So in the second step, this is now your electrophile, the carbon with the positive charge. This is the nucleophile. The reaction will happen between the electrophile and nucleophile. Draw the arrow from the nucleophile towards the electrophile. And that is the overall product in the reaction. You have added HX across the double bonded carbons. So the electrophilic addition reaction of alkenes happens in 2 steps. The first step, you form the carbocation. That is your reaction intermediate in the reaction. The second step, the carbocation reacts with the halogen to form the final product. Now among these 2 steps, the first step, the formation of the carbocation, is the slow step. Therefore that is the rate determining step. All right. Now the reason we call this mechanism as electrophilic addition mechanism because the first step in the reaction involves the attack of the alkene by an electrophile. That is why electrophilic. And if you look at the overall reaction, it is an addition reaction. Therefore we say this entire mechanism as electrophilic addition reaction. All right. So let's now take these 2 steps and put them in the reaction coordinate diagram. Always in a reaction coordinate diagram, you have energy on the y-axis, progress of the reaction on the x-axis. You're starting off with the reactants alkene, NHX. The first step results in the formation of the reaction intermediate, which is your carbocation. So always in an electrophilic addition reaction, the first step will be formation of the carbocation. That is the intermediate. This hill has its transition state 1. This hill has its transition state, which is transition state 2. It's a two-step reaction, therefore you have two hills. And I said the first step is the rate determining step. Therefore the height of that hill will be higher compared to the second hill height. Rate always depends on the height of the hill. Higher the height of the hill, slower the reaction. So among these two, this is the slower reaction, this is the rate determining step. It has the higher height. All right. The products. X and H. All right. So the reaction is overall exothermic. It releases energy because products are lower than the reactants. All right. So this is a generic graph for an electrophilic addition reaction. It will always be two steps. The first step would be the formation of the carbocation. The second step will be reaction of carbocation with X- to form the final product. The first step will always have the higher activation energy. So the height of the first hill will be much higher than the height of the second hill. That is the rate determining step, the first step. All right. So please make sure you get comfortable with this reaction mechanism. We are going to see this reaction mechanism with several different reagents, and the reaction will happen exactly like this. So if you understand this reaction mechanism, you can write the electrophilic addition to alkenes with any given reagent. All right. So we'll end today's lecture here. Please let me know if you have any questions regarding today's lecture. Have a good rest of the day.